lecture series. I'm Dr. Mark Swanson, Interim Director of the Oregon State University Research Forest System and on hiatus from the Starker Chair in Private and Family Forestry. Thank you all for being here this afternoon. I'd like to begin by acknowledging the Native peoples of this region and their connection to the land. Oregon State University in Corvallis, Oregon is located within the traditional homelands of the Marys River or Ampanefu Band of the Kalapuya people. Following the Willamette Valley Treaty of 1855, Kalapuya people were forcibly removed to reservations in Western Oregon. Today, living descendants of these people are part of the Confederated Tribe of the Grand Ronde Community of Oregon and the Confederated Tribes of the Siletz Indians. I would like to add that their important legacy in ecological stewardship is a key theme in today's lectures. The Starker Lecture Series began in 1985 with the objective of bringing thought-provoking and informative presentations about forestry, land management, and natural resource management to the public. Four generations ago, T.J. Starker founded prominent local forestry firm Starker Forests, and the Starker family and Starker Forests have played a major role in Oregon forestry, natural resources, education, and philanthropy. This lecture series is just one component of that legacy. Today, we have a special occasion to commemorate one of the Starker family. March 12th, 2025 would have been the 75th birthday of Bart Ball Starker. Bart graduated from the OSU College of Forestry, this institution, in 1972, and went to work for the family company. He was very active on numerous industry and advisory councils in the state of Oregon and on many other productive fronts. Bart received the College of Forestry's Distinguished Alumni Award in 2002, jointly with his brother Vaughn, who is in attendance this evening. Hello, Vaughn. Good to see you. And then later on, the E.B. Lemon Distinguished Alumni Award from the OSU Alumni Association. He loved the woods, and he also loved sharing the woods with many folks. So let's go ahead and thank the Starker family, both past and present, for their involvement, support, and generosity. I would also like to thank the Starker Lecture Steering Committee. These wonderful individuals deserve great credit for their efforts and creativity in bringing an engaging series to the college and to the public. They are Jessica Fontaine of the College of Forestry, Anna Starker May of Starker Forests, Julie Woodward of the Oregon Forest Resources Institute, Laurel Sherman, Assistant Professor of Practice of Forestry and Natural Resources Extension, and Dr. Annette Patton, Assistant Professor of Extension. So let's give these wonderful folks a warm welcome. And while we're here, I'd like to remind you that this is not the last Starker Lecture of 2025. On April 9th, we'll be having Daniel Bowker of the Northern Colorado Fireshed Collaborative talking about landscape resilience and restoration in that landscape. So same time, same place here in 117 PV Hall. Hopefully you can make it either in person or online. And now to introduce this evening's lecture. The Pacific Northwest Research Station of the United States Forest Service has played an important role in understanding the ecology and management of this, one of the world's most productive forest regions. This has been true since the days of pioneering early research ecologists Leo Isaac, Thornton T. Munger, and others. And the magnitude of the contributions of that institution has only grown with time. The diversity of the research topics, of course, has increased since those early days. Likewise, the diversity of the researchers themselves. In the intervening years, many nationally respected ecologists have worked for the Pacific Northwest Research Station, and today we are fortunate to have two of the most eminent of those scientists join us to discuss the land, the water, and how these interrelate in very dynamic ways. We'll begin in the water. Dr. Gordy Reeves is an aquatic ecologist. He was born and raised in upstate New York, fittingly alongside one of the world's great bodies of freshwater, Lake Ontario, and he studied biology at the State University of New York at Oswego. He and his wife then followed the setting sun to Arcata, California, where Gordy pursued an MS degree at Humboldt State University. And within 2 weeks, he says he and his wife decided that they would become Westerners on a permanent basis. Glad that happened, Gordy. After finishing his MS degree, he came to Oregon State to obtain a PhD in the Department of Fish and Wildlife with a dissertation on the effects of water temperature on the interrelationships of juvenile steelhead and headwater reach fish, the red-sided shiner. His postdoctoral plans were simple. Following graduation, he says he crossed the rugby field from Nash Hall over here to the PNW station right over there within sight of this building, where he spent the subsequent 38 years of his career. Dr. Reeves has worked on the planning efforts preceding the Northwest Forest Plan, as well as the Northwest Forest Plan itself. He was part of a team of ecologists and biologists that advised Judge William Dwyer of the Ninth Circuit Court during the days of the injunction against the Forest Service related to conservation of the northern spotted owl. And notably, he worked with Dr. Jim Siddell on a comprehensive aquatic strategy that would be an important part of the Northwest Forest Plan. At present, he's involved in a number of conservation-relevant activities, including advising the College of Forestry on matters related to the Elliott State Forest. So, Dr. Reeves, thank you so much for joining us this evening. Let's now step onto dry land for a fitting compliment to Dr. Reeves, Dr. Paul Hessburg. Originally hails from Minnesota, where he obtained a degree in forestry from the University of Minnesota. And just like Dr. Reeves, he has a PhD from Oregon State University, and this one from the Department of Botany and Plant Pathology. In those years, Paul pulled off a Herculean feat. He worked as a logger in the Coast Range to support a growing family. He held down a research assistantship as well here at the university and completed a PhD all at the same time. Dr. Hessburg went on to work as a research landscape ecologist for the Pacific Northwest Research Station based in Wenatchee, Washington. His science has ranged very widely in terms of topic, but with a very strong theme of landscape pattern and altered disturbance regimes, especially focused on the inland region of the Pacific Northwest. In 2018, Dr. Hessburg received the Distinguished Scientist Chiefs Award, reflecting his prominence in forestry research at a national level. And this afternoon, I believe we will come away with the sense that we cannot consider either the land or the water in isolation from each other, but together. Holism is not merely a nice catchword, but it describes what we must do and what we must be to succeed in conserving our landscapes and by extension, much of what we hold dear in this region. And so without further ado, please join me in giving a warm welcome to Dr. Gordy Reeves and Dr. Paul Hessburg.
It's a privilege to be back home. Thanks for having us here. That was such a great intro. Let me start and say, is there any questions? Because I think you solved the riddle right there. So we're going to do something a little different here. You're going to see an awful lot of stuff coming out of my laboratory and probably 40 or 50 partner laboratories. And so we're going to tell you a story that we've woven over the course of our career about learning about how aquatic landscapes work, how terrestrial landscapes work, and how they're connected, deeply connected by processes. And hopefully by the end of this talk, we'll have you scratching your head over the question of whether or not there's an aquatic ecosystem that separates from the terrestrial ecosystem. We find that there isn't, that they're one linked system. And so this is a story about that. Before we started putting out fires, there was a tremendous amount of fire on the landscape. And it doesn't start with fire suppression. It starts with the loss of indigenous cultural burning through diseases, Euro-American diseases that wiped out 80 or 90% of the indigenous presence in the United States. So estimates are between 15 and 25 million people were living on the landscape. Bigger estimates also abound, but there's disagreement. This went on for 10 to 15,000 years. There's new evidence on the Oregon coast that Paleo-Indian settlement happened between 13,000 and 17,000 years ago. And it's even longer when you get to the Northeast and Eastern United States. It's a lot of generations of people tinkering with the landscape and learning stuff and passing down the stuff that works. History teaches us that westward colonization itself was facilitated by the extent of cultural burning. Folks got through the woods, they got through the mountain passes because they didn't have to clear much on the way through. Closed canopy forests, in fact, reduced food and resource and medicinal resources in forest understories. So if you think about it, in the interior, forests live where the snow lives. And there's time release water. And if you open up a canopy and you put sun on the ground, you got a grocery store. And so it was the understories in so many of the forests or in the prairies that were food production systems, and they were vast. A lot of the ethnobotany studies right now are showing what it takes to be able to feed a family group or a tribe. And it's a vast amount of resources. And the landscape was fully occupied under that lifestyle. Absent fires, fires have grown a lot denser, and it's affected traditional food gathering and the way the forests look. I'm going to show some slides about that from the interior, from the coast range, from the west slope. They're now highly encroached by forested land cover. One of the take-home messages, there were a lot of non-forest elements on the landscape that were produced by lightning and cultural burning. Things like burn bare ground, early cereal forest conditions were quite extensive, a lot of wetlands, a lot of wet and dry meadows, a lot of shrublands, a lot of open canopies, sparse savannas on the landscape. And this was the intermarriage of cultural burning and lightning burning, and it was a big deal. Many non-forest areas were these meadows and prairies where plants and material resources and medicinal products were available, but there was also burning to improve the forage conditions for the ungulates that were harvested, because there was a pattern of moving from place to place. And so making sure the forage was in great condition was also critical, sort of take care of the landscape that takes care of us. So the idea that humans lived without fire and can continue to live without fire is not only contrary to fact, it's contrary to history. Today, there's a large fire deficit. Bill Leanhouse from 1998 calculated using Kukler vegetation types and their disturbance regimes that in an average year, 45 to 85 million acres burned in the United States, and it was not mostly high severity. It was fire that skiffed off fuels. And so at a subcontinental to a continental scale, fuels were more limiting than we can even imagine, surface fuels. That's the reference if you're interested. So the next thing I'm going to do here is going to go through some examples, kind of a survey of interior and west side forest types, and to show you some of the things that are going on. This is an interior example of a frequent fire system. This is a lot of ponderosa pine, some Douglas fir. Most of the fires were low severity. By that, I mean fires took 20% of the trees or less. Most of the time, hotter fires, when there was a longer interval between fire, were moderate severity, but they didn't take as much as moderate severity regime shows. So in that 25 to 35 or 40%. And so here I've got a tri-photo that's basically showing you from the 1930s. Let me get rid of this bad way. The open canopy conditions that you can see, all of the black and whites are from the National Archives in Seattle. And then all the color photos are by a colleague of mine, John Marshall, who goes back to these fire lookouts, finds the exact place and rephotographs them. They're all in the 2010s, 2020s. You can see how fires expanded on the landscape in that middle photo. On the bottom photo, you can see very widespread stand replacement fire, which was altogether atypical for this particular landscape. One of the things I want to tie to Gordy's presentation is to talk about a couple of the features that are really important. Fires in these systems were not stair-stepped, didn't produce stair-stepped edges. They produced a feathered condition where a fire ramped down or ramped up over 100 to 300 meters. So there's this texture of highly networked edginess across the landscape that we think was probably pretty important for critters and certain plants as well. That's really changed. It was very difficult to be able to get hydrophobic soils that would affect nearby streams from these kinds of fire regimes, but occasionally you'd get a more severe fire and you get sediment and wood and debris into nearby streams. So these frequent fires were an important stabilizing influence. Low severity fire that was frequent tended to beget more of the same. All right, moving further up the hill, this is from Duncan Hill. It's looking down at the Columbia River. It's about a 330,000 acre look. And on the top photo, I just want to show you, these are moist mixed conifer forests where you can see so much patchiness and absence of tree cover. This is a pretty significant thing. And the more we look at these photos from the National Archives, we see this repeated in the dry and the moist cover types. The moist cover types have less frequent fire, 20 to say 50 years. And because of that, there are more fuels. And so the fires tend to be moderate severity, take some fires, a coarser grain to the landscape, occasional severe fires like you can see on the bottom left there. Again, most of the patchiness had these feathered fuzzy edges on it. And most of the patch sizes were small to medium size with these feathered edges. And what was the stabilizing influence at this scale and in these forest types was there was a lot of patchiness. And so that was throttle control on fire rate of spread, flame length, fire line intensity, and crown fire potential. So it was the patchwork itself that produced a sort of mesoscale stabilizing influence. These are cold forests. So in the previous example, moist forests are western larch, lodgepole pine, Douglas fir. In the first example, it was ponderosa pine, Douglas fir. These are cold forests in the interior again, with fires as frequent as every 30 years to as every 150 years. A lot of meadows, a lot of non-forest. The top photo, you can see, as far as the eye can see, it's a 120-degree panorama. There's a lot of area that's in hardwood forest, recently burned and recovering. And this was fairly typical. We're refinding this pattern in our modeling. You can see how there, in the absence of fire, there's a lot more wall-to-wall trees. If you look on the upper left of the top photo, you can see that there are avalanche chutes that are making it all the way to the stream that are delivering goodies to aquatic habitats. You can see in the modern scene, none of that's going on whatsoever. And the big absence is fires. Here's at some of the highest elevations in the interior. This happens to show upper tree lines. So you think about white bark pine, subalpine larch in the high country. And then below that, lodgepole pine, subalpine fir, Engelmann spruce. These were copse in ribbon forest, basically. With mostly these landscapes were wet and dry meadows. And the wet and dry meadows cured out and they actually delivered very often fast, low intensity fire so that you'd see fire scarred lodgepole pine, Engelmann spruce, and subalpine fir in many of these systems. And in this particular landscape, we saw fire scars, at least 5 fire scars on some lodgepole pine in the system. So fire can condition lodgepole pine, so it's not just a boom or bust system. So the hill slope erosion processes were pretty gentle in this country, not much hydrophobicity. And I want to beam in here real quick, just to give you an idea of the, in 100 years or less, the amount of trees that have filled in the interval between fire to show you just how widespread the wet and dry meadows are. We actually sampled in this ecosystem and there are between 100 and 1,000 times more trees in it than there were less than 100 years ago. Let's move to the west side right now. Here you can see this is in Yamhill County, Bell Mountain. On the lower right, you can see the location. The next vicinity map is basically showing you a complete absence of fires since 1900. What I want to show you in the top photo is that it was really quite varied, successionally varied. The ridge tops were actually intentionally burned. An awful lot of the movement of tribes was actually using the ridge network and the valley bottoms. And so what you can see is that these feathered edges are really fairly common, more stair-stepped edges in the current predicament. And hill slope erosion tended to be pulsed when the fire severity was a little bit greater. You'd see hydrophobic soils, and when it was not, you would not see hydrophobic soils. There's been little fire since 1900. Guess where this is? This is really close to home. This is Mary's Peak. Looking north, and this is a 120-degree panorama. And as far as the eye can see, the ridge tops and the south aspects are basically grass balls. At that time, so much burning was going on in this territory, and we now see it's completely covered with a nap of trees. Again, no fires since 1900. There's the location map. This was an incredible grocery store for food production. It was really, really important. So there was much burning that maintained it. Some of it still is present today. You can see the remnants of that as you move through the Coast Range. Again, the patches were fuzzy. You can see feathered edges going from forest to non-forest and so forth. East wind events occurred every now and again, and they burned massive areas of the landscape. You can see the location. This is Little Mount Hebo. This area is affected by 3 burns, one in 1840, one in 1910, and I think the other one, the last one was in 1940s, something like that. And you can see that most of the 3/4 of the right side of the photo has been burned and regenerated. And then in the background, you can again see those textures of different successional classes, open and closed canopy in that landscape as well. These kinds of fires produce massive hydrophobic soils, and they're really important for reorganizing the channel, producing a sediment budget and a wood budget for streams. This is the map of the Coast Range. You can see in the vicinity map on top there, the part of the Coast Range I'm talking about in Oregon. The big fires are going to be the big eastward events that have occurred between 1850 and 1940. And one of the punchlines here is that before 1940, a massive amount of the forest was actually young and intermediate age as a consequence of big fires and then the early logging that happened. And so by 1940, this landscape was already incredibly changed as a result of small, medium-sized fires and then the big east wind events. All right, and here's what it gave us. And Gordy's going to unpack this quite a bit more. But an awful lot of the tributaries, the trees would fall in, you'd have debris flows, shallow mass failures that would fill the channel, and you'd have a channel reorganizing event that would take the rocks, wood, sediment, root wads, trees, and put them down the tributary, and they dump them in main stem reaches. They move the river around, they change where the channel lived, they put braids in streams, they built alluvial fans that were incredibly important. And here's a look at upper left is a west side stream where a hot burn produced hydrophobic soils. And it looks like a mess, right? You can see soil floating on the water there, but that gets reorganized fairly quickly. Down below, you can see the middle fork of the Salmon there after Boundary Creek blew out. I was in a raft the week that it blew out, and we had to wait for them to blow the log jam there so we could get through. Bottom middle is a look at that from the air. The bottom right shows in a few short years how the spring freshet moved that wood and created habitat for days down the river as a consequence. The year we floated this, we were getting out about every 2 miles to stop and gauge where the strainers were so that we could even get down the river. It's not that kind of river right now, and it happens really fast. So it looks like death right when it happens, but it's such a good thing for the ecosystem. Top right is the Selway. High Country Lodgepole pine burned, fell apart, big debris flow that came through, filled the creek in the bottom, and it keeps putting wood into that valley bottom. All right, Gordy's going to do a thing here, and I'll sit down for a second.
Okay, thanks, Paul.
Yep.
So Paul's done a very nice job of setting this up. I think the question is, so you see all this reorganization that's going on. What was going on in the aquatic system? Well, as Paul pointed out at the beginning of what is going to be a really productive. We think about how we view fish and fire. These are some posters the Forest Service had put out, some headlines from the Oregonian. Generally, we hear fire and fish in a very negative connotation. Fish die after fire because it destroys the ground cover, streams and rivers get filled. It may for a short time period, but what we have to do is take a bit of a longer view here. Wrong one. Okay, so first of all, let's think about the adaptation to system has. The riparian vegetation is going to respond quite quickly. It is highly adapted to fire, and you can see the mechanisms here that work that Kate Dwyer and Boone Kaufman have done. So the riparian zone can respond relatively quickly to these type of events. But the important thing is to ask, how are the fish adapted to them? Well, if we look at the fish that we're particularly interested in, either that we look at the native salmon, they're highly adapted to these dynamic environments. Okay. One thing is, if we look at them, they have incredible flexibility from a genetic perspective, which allows them to adapt to a wide range of conditions. The other thing is straying of adults. Now, in the aquatic world or in the world of fish, when you say straying, that's usually considered a maladaptive thing, and it usually is associated with hatcheries, where hatchery fish don't return to the hatchery, they end up with the native populations, and there's consequences of that. But think about it from a population strategy. If you're in a very dynamic environment, a place that is unstable and unpredictable for some extended period of time, the strategy of the population is everybody isn't going to return. You want to continually be putting seed sources out to find these new areas that become available in the landscape. And that's exactly what these fish are doing. Up to 25% of populations of Pacific salmon stray. They're not, the story we have, or what we want to believe is, where that fish spawn, the adult spawn, the juveniles emerge, they go to the ocean and they come back to that very spot where their parents had spawned. That's not true. There's a segment of them that do, but there's also a major segment that don't. And you think about that, it's really important adaptation when you're in a very unpredictable environment. The other thing we know is these fish have a high capacity to reproduce. They are preventing spawning fishes for fish that put their eggs in the gravel. These fish have the highest, what's called fecundity, the number of eggs per unit weight or length of any other fish that do that thing. So they have a potential to find these new areas, and with this trait, this high fecundity, they can colonize it very quickly. So they can reestablish the population. The population isn't going to be dependent on the same particular place through time. It's going to be seeking new areas, and it's highly adapted to doing that. The other thing is about juveniles. I remember when I started school back when, here and before that, there was a lot of work coming out of Oregon State about juvenile salmon, as an example, coho salmon. This was Don Chapman's work. And he identified in coho salmon, he identified these fish that emerged and moved. He referred to them as nomads. And they were considered maladaptive fish that weren't going to make it, and they just left. Well, it turned out we now know that, again, from a population perspective, there's a whole host of life history strategies in these juveniles, and they're moving all the time. We have fish that are going to remain in the stream for an extended period of time. They may remain in the stream for 6 months and then move. They may remain in the stream for a few days and move. So you think about it, again, this is a strategy for finding these new areas and helping maintain the persistence of these populations. Populations don't have to persist in the same place through time. They simply couldn't. They had to have strategies that allowed them to exist in this very dynamic environment. Here's an example, and there's a lot of information here, but this is some work from folks at Montana State. And really, we just want to circle in right here. So what we have here are the native cutthroat, west slope cutthroat, bull trout, and brook trout. And notice this is this particular these type of streams. These are ones that saw the most disturbance. There was a fire, and there was a subsequent debris flow following it. You notice what happened is the native fish, they decline and then they come back. The non-native fish, the eastern brook trout, declines and doesn't recover. So it's like the native populations are highly adapted. And what it was there were life history types in these two that simply moved in to that area and recolonized it. They had been moving around the landscape and they found these new areas to persist. This is some work done by Jason Dunham and others showing what happens in terms of streams post-fire. Immediately following fire, there's major changes in the stream in many systems here. And these are ones that are not necessarily detrimental, but they're ones that can be capitalized on by the population. The input of nutrients, with suspended sediments. Now we usually think, well, we don't want to see suspended sediment. But one of the things we need to keep in mind is suspended sediment is turbid. And we said, well, the fish aren't going to feed. These fish, if you start to look at their behavior, they're highly flexible in how they feed. And during periods of high turbidity, they're not feeding in the water column, they're moving to the bottom, and they're doing quite well. So they're highly adapted to these types of situations. And then, you know, within a few years, the invertebrates in the system are popping up, because now you've got the input, you've got light coming in, you've got primary production increasing, you've got a lot of shrubs and other types of non-coniferous vegetation that's contributing to these streams. And you can see that as a result, there's going to be an uptick in the productivity of these systems. This is some really neat work, again, by Jason Dunham and Amanda Rosenberger, looking at the response of resident trout to fire. What you have again is this unburned, burned, and then burned and disturbed, okay? And what you, then the different age classes on the bottom axis. Look where the highest productivity was, in terms of the largest fish were. They were in the areas that were the most disturbed. Of each of, you know, in each year, each age class. Again, there's a change in the way the system is operating, the productivity and stuff, and it looks like these fish can take advantage of it. What's most interesting is they, again, looking at the age here, age 0, you see even at a very young age, some of these fish are reaching sexual maturity, so they're capable of reproducing already. Where in the unburned area there was none. Then you go to the age 1 fish and look at that. Within 1 year, a large segment of that population has reached sexual maturity. Okay, and then by the age 2, then it starts to even out. But what you're seeing is these fish are responding to that fire by growing quickly and being able to reproduce at an earlier age. Very, very significant changes. Okay, I'm going to turn it back to Paul.
Thanks, Ray. So I wanted to show some more west side examples. This is Beaver Lookout on the Siuslaw National Forest. You can see its location in the Coast Range lower right there. The number of fires that have occurred since 1900, second to the right. And this is a landscape that's actually dominated by the native hardwoods after disturbance. So there's a lot of disturbance going on there, a lot of red alder, a lot of maples on that landscape. And increasingly what we're finding about these hardwood conditions is that they were not only interior and west side, they were very present. These are early cyril species. They're prolific, either clonal species or cedars, and they're the first trees to jump out of the hole. So here we're looking at quite a bit of alder. And again, you see forests not dominating the landscape, conifer forests, but you see them as stringers on that particular landscape. There's an awful lot to be gotten if you're an indigenous tribe or a family group working in this particular landscape. It was not a landscape where you typically get really severe fire because of the moist conditions afforded by the hardwoods in between the patches of conifers. This is another Coast Range location. You can see its location further south in the Coast Range. This is Cannibal Mountain. You can see tremendous pattern in heterogeneity in successional conditions and the amount of non-forest conditions that occur. Again, pretty commonly the ridges were burned and treeless. This is a look at some country in the Siskiyou Mountains. You can see it low southwest. You're now getting into moderate to frequent fire, and the fires tended to be naturally big in this landscape. So instead of having tens and hundreds of acres, you tended to have hundreds and thousands of hectares of fires. And that was what allowed the granularity of the landscape to develop. And these areas, because they were so incredibly steep, it was the ridges and the ridge systems and the way they networked that were used by the indigenous folks and the valley bottoms as well. But these were also significant governors on how big fires could get and how hot they could get. when you had these high severity patches, there was a lot of debris torrents, shallow mass failures, wood and sediment budgets contributed to streams. On the right, you can see what fires have looked like in this country in the recent 25 years. All right.
Okay, so I want to come back to the coast range here and talk about the effects of fire. So this, we did back in the early 90s, we were particularly interested in what was going on with disturbances. And we tried to find streams in the coast range that didn't have a heavy human signature, and we could look at the what the natural cycle may have been in these streams. So these are all sample sizes of 1. Because it's really difficult to find large intact watersheds in the coast range that haven't been affected. But nonetheless, what this represents is probably likely the range of conditions that streams may have experienced. So what you see up here is a stream that was, by our best guess from the vegetation, was somewhere in the neighborhood of 50 or 60 years post-fire. Paul was talking about these major deliveries of sediment and wood to the channel. We usually think of that as being sort of a chronic process. It's a catastrophic process. You're in it, you're delivering via landslides and hill slope failures, tremendous amounts of material to the channel in these fires. This is one, the sediments were roughly 2 to 3 meters deep. And there was very little wood that was visible. There was wood entrained in the system, in the gravel, but not anywhere else. And then right next door to this was a system that had burned, by our guess, somewhere 140 to 160 years ago. And it had a combination of sediment sizes, a fair amount of wood, but it had the highest number of fish and the greatest diversity of fish. Okay, in terms of, and then we went to old growth systems in the coast range, in the coast. There was a tremendous amount of wood, and it was big. But there wasn't much in terms of sediment. There was a lot of bedrock, a lot of larger substrates in those systems. These systems hadn't been disturbed for a long period of time. And subsequently, there was in terms of fish productivity, this was quite low. But think about what we're trying to protect under the guide for aquatic purposes. We want to protect old growth streams. And I think if you think about the history of the coast range, and probably other places as well, old growth may not be the objective for if we're looking to conserve fish, and we get and I can be, I'll attest, it happened to me. You draw a line on a map, and you think, oh, I just saved fish, you know. I don't think that's going to be the case. You've got to really rethink that type of thinking. Yeah, like I said, this was it. This was the best habitat conditions that we saw. By our best guess, somewhere if you looked at the coast range historically, 40 to 60% of the watershed was probably productive for fish at any point in time. Now that was shifting, of course, just like the forest. But we didn't have fish everywhere. The idea that you could have walked across the back of salmon in any stream in the coast range historically is a fallacy. It's never happened, and very likely it never happened. And so it was just this middle, and what Paul was talking about, it's interesting, lined up just with what Paul, the age of forest that Paul was talking about, was most dominant. But we've got to, I think we need to challenge some of our assumptions that we've made about what we're doing and where. Okay, we do the same thing on the east side. This is some work on these wet meadows. Paul, spoke to them. This is some work that Pete Bisson and Steve Wandell have done about the effect of fire. Where you have these wet meadows, absent fire, the channel begins to downcut. And then eventually the water table drops, and you go from a wet meadow to a forest in these areas, which is some of the things that Paul was showing. And it turns out that fire is really critical, because what you have fire, and then you have flood, and the introduction of those sediments from the flood begin to erode the water table, or the stream bed and begin to raise the water table and reset the meadows. These meadows, you know, again, the cycle of disturbances was really critical. Think about the first thing we do after a fire. One of the first things we attempt to do is stop erosion. That's one of the primary objectives of the BEAR program, is to stop erosion. Under the guise of, quote, protecting the stream. I would say we need to begin to re-examine it. Is that really critical? Because if we want to restore our wet meadows onto the landscape, and these are key ecological places to have. Probably the worst thing we can do is go out there and stop erosion after fire. We should allow erosion to occur where we can. And so again, thinking about these systems in a different way and thinking about the processes that are creating them are really going to be crucial. And if we're going to really make a difference, we're going to have to challenge the way we think. Okay.
I want to move to the west slope of the Cascades and feature some work of colleagues in the room here and some of their former students. On the left, Tom Spies led a group of folks where we took a look at the forest type maps you can see on the far left. We reinterpreted from the data between the start of the Northwest Forest Plan and the present day, the fire regimes. And what you can see in the Coast Range and the west slope of the Cascades, there's an awful lot of fire that is moderately frequent, mixed severity. And this is gleaned from many studies that we included in that Frontiers paper. This is work by Tom's student, Alan Tepley at the time, where he did some landmark work. And it's amazed me that this is not a more cited paper. It's 25 years ahead of its time. What he's basically showing you within this area is that most fire within the area he studied in the western middle Cascades was moderate severity fire and even low severity fire. Only 25, 1/4 of the fire was stand replacement fires. And those moderate severity fires were either begetting more moderate severity fire or in many cases cultivated repeated burning. So you actually had low severity fire development pathways. And so what he's done here is he's drawn pictures of the kinds of forest conditions that come out of that. His message was there was a lot of fire, it was moderately frequent, and it was creating forest conditions that are not the result primarily of boom and bust fire ecology. This is work by Matt Riley and others here from a recent book that we put out. Again, taking a look at these forest types within this area. On the left side there, you can see that he's looking at the relationship of elevation, precipitation, and temperature within those mapped areas of vegetation. In the middle, he's showing the Willamette Valley and how much of it was in prairie and savanna and oak woodland a long time ago. And the closed canopy forest was much less than we see today. And the dense oak woodlands were less common than the more open oak woodlands. And they talk about, they refashioned some of the fire severity mapping in this piece as well. They show the likelihood of dry east wind events, where are the places that have the highest recurrent, really windy conditions. And then the lightning ignition zones. And so what they're interpreting in this work is essentially why we find the spatial distribution of fire severity on this kind. It's an important piece, I think, to look through. More recent work by James Johnston, Andrew Merschel and company. You can see the geographic locations on the map there of the sampling. What they're basically finding out, so you can see the fire frequencies on the far right there, and you can see in simple schematics just how much fire was in Douglas fir, which is in these Douglas fir hemlock types. And also in grand fir types. So frequent to moderately frequent fire coming from those fire history studies. Additional work by Andrew Merschel. This is stuff you really should read. It's quite excellent. Again, you can see in the vicinity map, Cascade southern region, And if you look at the legend here, Douglas fir is in red in this. The hash lines are fires. They're either fires where the sampling occurred or they're fires nearby. And what they're basically showing you is that Douglas fir is an incredibly difficult species to get fire histories from. And even in the interior where it's fire scarred, they always pick the ponderosa pine next to it. So the work that's being done by Marshall and James Johnson is incredibly important work, and it's difficult work. What they're finding out is there was a lot more fire. There were a lot more areas or times when there were concurrent fires across a big landscape. And if you think about Templey's work, basically saying that you set in motion in the case of reburning, that one fire and its severity has an influence on the next fire and its severity. And so the vector of fires in a reburn cycle are really critical to the structure and the development of forests. All right, I'm going to give you some take-homes for fire ecology and forest variability. In the interior and on the west side, non-forest and hardwood forest elements are incredibly important. And they were the result of lightning fires and indigenous burning that was going on. By non-forest, I mean recently burned bare ground. There was a lot of that. Early soil conditions where early soil trees and hardwood shrubs are shooting out of the ground first. Open canopy conditions, wet and dry meadows, prairies were incredibly abundant, shrub fields were abundant, and wetlands. When you take pumps off of area that is wet and has a significant amount of water associated, you find wetlands coming back. They're transpiring so much water and dewatering the soil they're on. And so many wetlands are currently hidden across that landscape. They're very influential to how the landscape burned historically. What we're learning in our heavy lifting modeling process is that there's a tug of war going on between factors growing forests and taking them away. And the major disturbance taking them away is fire. And what we're seeing is the highest stored energy on the landscape is in the forested condition, especially multi-layered forested condition. And many of the same factors that make an area productive and capable of growing a forest are the same covariates that take it away during the fire season. So this tug of war is constantly rebalancing in each turn of the climate. What kind of forest arrangements have inherent stability or an instability associated with them? So this is just some of the stuff that I said. Incredible areas we're finding in these fuzzy edges, I think, in terms of wildlife and plant habitats. It's really important for us to take a deep dive into what is the relevance of these fuzzy edges that we create. A lot of species can make a living in them, and that's typically not how we create forest edges. Fires take a while to ramp up. Fires take a while to come down, and we're finding in our modeling that those are 100-meter to 300-meter widths very often. And they're networked really well, so things can move within the network of fuzzy edges really well. East side and west side, we're finding that anadromous and cold water fish, they evolved with fire, more fire in the interior. As we get higher and colder, there's more high severity fire, and more of the landscape was not forested as a consequence of this potential energy tug of war that was going on. So an awful lot of our fires right now are massive because those burned and recovering patches are not on the landscape. These fires catalyzed important hill slope processes that delivered wood and sediment budgets to streams. And so one of the things that I would argue in my handoff to Gordy is to basically say, how could fish have lived without a highly dynamic landscape? And if it was dynamic in these ways, how would, I think you refer to Pacific salmon as dandelions. They've got an app to do anything, anywhere, most of the time. How could you imagine that they don't have an app for making use of what happens as hill slope processes dump wood, sediment, cobble, and root wads, and then get sorted over time? It looks to me from a hill slope and terrestrial fire process that they're creating the secret sauce for aquatic habitat succession in pulses across the landscape in different spaces. And so one of the things that's intuitive to me from a fire ecology and landscape ecology point of view is that it's intuitive that restoring an active fire regime so that you don't have to be afraid when fire comes into a landscape. You can actually accept more flavors of fire. That's a good idea, not only for climate and wildfire adaptation, but it's probably a good idea for fish. All right, and with that, we'll end our comments, and we've got time for questions. All right. Question.
I have a question.
Yeah.
So, great presentation, by the way, thank you. I worked for the Forest Service for over 40 years, and part of my experience was on the Science Law. And I also worked on the PAD and Boise National Forest in the 1980 to 90 range and now 2015 range. But I saw a lot of fire, particularly in the interior areas of Idaho. And one of the things I wanted to ask you is, what we saw on those interior Idaho forests, basically, which are mostly dry ponderosa pine, dried up fir, and then you move up into the higher lodgepole pine, dense stems. Is we had, for 2015, we had about 80 to 400,000 acres that burned per year on those respective forests. And so now the big question has always been, what do we do with those acreages? Some was high intensity, a fair number was high intensity. Some was, obviously lower intensity, water intensity. There was massive movements of soil and vegetation on the rivers. And then when you look at the particularly salmonoid interests on the South Fork of the Salmon River, the Middle Fork of the Salmon River, the main stem of the Salmon River, kind of what would be it's kind of what you said at the end is like, what do we need to start looking at from a fire regime when new fires start in these now burned areas? And there's a lot of acres that are burned.
Yeah, I'm real familiar with Boise and Payette fires. There's a lot of uncharacteristic fire that went through those landscapes. And a lot of the recent work is talking about burning the burns, even where you had high severity fire, and start recreating a patchwork of conditions that will not result in a worse fire in the second fire. There's so much wood going down right now, and we can't have it all on the ground and going off at the same time. So there's an awful lot of folks basically saying wildfire is doing more work than anything else on the landscape. What is the work of wildfire? Is it very good? My answer to that is we've been through all the MPBS burn severity data since 1984, and about 50% of the acres are a pretty good first entry fire. I would say keep the magic going with those. If you got the door kicked open, keep it open and keep laying fire down. The other 50% needs some kind of hand down. And when you've got big swatches of high severity, breaking that up so it doesn't go at once and putting the kind of fire that burns up the kindling fuels from this size down, chars the big wood but doesn't smolder it. That sort of thing is going to be needed. But I don't think, I literally think managing the post-fire environment is job one right now, because it's working the most acres, 7 million acres in an average year right now. About half of it's fire we wish we didn't get, right? And then the second thing is, I would say that we have to start not putting out 97, 98% of the wildfires. Easiest fires to hook are those that are occurring under moderating fire weather. And some of those could do really good work. So being able to set up a landscape where you have burn planning, you understand the situation, you've done some work to basically harden areas that you can anchor and control. Fires within pods right now that folks here at Oregon State are doing a lot of work with. Having conditions where when fuels are available to burn and taking fire for a walk more of the time where you can actually hold it, release it, turn it, that sort of thing is going to be an important thing. We're going to drop a paper pretty soon that basically says that the post-fire environment and the managed wildfire environment is the kind of scale of work that you actually have to do to be able to reduce the work of wildfire. Being more strategic with the thinning and the burning, but writing a new script for how we think about wildfire is really important. And then looking at the work of wildfire and using the best of it at full advantage. We simply miss that in a decade, that's 35 million acres right now at the current pace of wildfire. That's a big deal. Hopefully that helps.
And I think, it did, and to me, it's like that edge effect and that the benefits of having that kind of feathered edge. I mean, that to me is one of the goals always of kind of when you look at managing fire in some of these big burned areas, if you have the 100-acre patch or the 300-acre or the 1,000-acre type of deal with different intensities, that would seem to be really one of the ways to achieve maximum productivity for kind of a lot of different resources.
Yeah, we're thinking that we're just exploring the feathered edge idea, but we're thinking it's probably a big ingredient in more resilient landscapes. And it networks incredibly. So if you're small, medium-sized thing trying to make a living and you want a salad bowl of ingredients in close proximity, these feathered edges seem to provide that. So we're going to go exploring more there. Other questions? Yes, ma'am.
I have a question for Gordy. Gordy, your talk about the resilience of the fish based on their ability to repopulate areas. How can you put that in today's context where we have a lot more barriers to fish movement?
Yeah, well, I think part of this is the population has to retain that capacity to respond. And one of the things is, think about what we're trying to do under the guise of conservation and recovery of fish. It's all about more fish. We have to get back X number of fish. But the reality is, what we should be thinking about is making a landscape that allows these fish to express this diversity. And in both, and particularly of juveniles, so they can move around the landscape and allow these life history types to play out. But one of the things that has to accompany this type of effort is allowing that movement, providing the means, there's non-impediments that the fish can move downstream or they can move off channel, whatever they need to do. We need to start thinking about setting that up, setting this landscape up so that diversity can occur and be expressed. And that, and that means you've got to provide the opportunity for that to happen. And that's not what conservation is all about right now. The conservation and ESA is all about numbers. We're gonna get, X number back. But think about it, particularly in an uncertain future, not just fires and all the other things. If you're going to persist, you want to have some diversity. The ability for the population to express this diversity so that they can respond moving forward. And that's a very different approach to thinking about conservation than what we do. Well,
I was following up on your question about passage, and I work with a watershed council up in the north coast of Oregon, and we were focused a lot on passage, and we had an interesting situation. We had a landslide dumped into a small creek, and we had identified through previous work that a culvert was a very bad culvert, it didn't provide fish passage, and it had okay fish habitat above the culvert. After the landslide, about a mile upstream, they're like, wow, this fish habitat looks really fantastic, and this sediment has made the culvert passable. Steve Trask pointed out, who's done a lot of work in the Coast Range, that the people who put the culverts in weren't stupid. But sediment and channels, not only do they move laterally, they move vertically with sediment. And as you're planning and managing infrastructure, you need to keep that in mind. Downstream from one of your photos, Gordy, on Camas Creek, I came up with a rough estimate, this is between Ukiah and Starkey, that roughly 50 and 200 5-yard dump truck loads of material were missing that would be required to recover the kind of meadows that we were interested in. And at the time, most of the focus on those channel morphologies had to do with what was going on in the banks and grazing, which can be important. But at the same time, the Forest Service was attempting to suppress upstream erosion and wasn't trying to manage things that could create sediment storage capacity in these larger trunk channels. And so when you're thinking about that, it's context. Both sediment and fish exist within channel network contexts, and they move. Anyway, Bob?
Yeah, the question of context and holism. I never, I didn't hear any mention of beaver, for example. State of Oregon like most of the American West, decimated beaver populations in the 1800s. And so long before you got concerned about your fires, beavers were gone. Okay, we've made no effort essentially in this state and many places in the American West to bring beavers back. If you ask me, how many beavers do we have today relative to what we used to have? My best guesstimate, and I went back to try and look at this, we're maybe at 2% on the west side. We're at 0.2% on the east side. You run a fire through an area with beaver and you run a fire through an area without beaver, I would argue the results in the stream will be incredibly different. And yet, there's been no mention of beaver here. It's basically an upslope look at what's going on with fire and nothing downstream. If you want wet meadows, you bring beaver back. You want biodiversity along streams, you bring beaver back. If you want to trap sediment for habitat, you bring beaver back. And it's a huge, major missing component in Oregon stream systems.
It is.
And so from the holistic standpoint, I think it's a missing component.
Yeah. Yeah, we have it included in other talks, but we were trying to pay attention to time and having a decent Q&A. But during the Columbia Basin Project, Jim Sennell went through the Senate record going back into the 1800s. And he estimated that the interior Columbia Basin, so east side Oregon, Washington, most of Idaho and northwest Montana had between 6 and 12 million beaver before beaver. And there's new work coming out right now that suggests that there were 60 million beaver in North America before trapping. So incredible engineering, incredible landscape ingredient for fire ecology as well.
So how does that change your story? If you're looking at systems today with fire and you're talking about stream effects and things like that, and we're looking at streams without beaver, I mean, is it really the way we should be thinking about these stream systems?
It's incomplete. I mean, having widespread beavers is, while contentious, it was incredibly important to influencing how fire flowed on the landscape. I do a talk on the criticality of non-forest, and beavers are in that talk in terms of how they influence the spread and flow and intensity of fire across the landscape. And at those numbers, it would have been an incredible influence, not only to the availability of wetlands that were there, but also massive areas of water that just had to be spotted around or just simply stop fires. Yeah, it's a huge idea.
More beavers.
Go Beavers.
Go Beavers.
Great. So I worked for the USGS Western Fisheries, and we did a lot of work with them. It's about 2 years ago, there was the McKinney fire. There was that big landslide that hit the Klamath. It was like in the high country news. It was in the LA Times. And all these articles was universally sort of painted as a bad thing.
Mhm.
And I'm on this email string with all these fish biologists. They're all having the same feeling, like pictures of dead fish. Because I've seen your talk before, so I reply like, "Oh, this is great." And the response is like, "I'm celebrating carbon." So like, am I wrong? Like, is that actually potentially McKinney fire and that landslide providing benefits down the road? And if so, how do you change that perception of landslide bad, fish kill bad because it killed fish this year?
Well, it's interesting. We had some real fun conversations out on the darker land. I think what we have to do is fundamentally go back and ask ourselves, why do we say that's bad? Or why do we say that's good? And go to the very foundation from which we make those opinions. And I would argue that we have these different perceptions because we have the aquatic people have a very different perspective on the world than do the terrestrial people. And what I mean by that, think about what shaped our thinking about aquatic ecosystems. The river continuum, bog and channel types, and regulation, right? I mean, think about the regulation. You come up, there's one standard, you're supposed to have this many pools or this many pieces of wood, and it's expected that happens everywhere. And if it doesn't, we construe it to be negative. If you think about how the terrestrial part of the landscape is thought about, succession is, there's this idea that there's a variation through time and space, right? There's no parallel concept to that on the aquatic side, because we have no concept of the the underpinning for aquatic perception, lack time. And if you don't have a perception of time, you can't think about change. You think everything is static. And I think that what we really have to do, and I think it has to happen sooner than later, is have an honest and discussion about the differences of opinion and why we have them, and about our assumptions that we make, the assumptions we make about aquatic ecosystems. And test the dog, for example, all the fish return, the adults return to that same stream, blah, 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 right? We know that's simply not true. We know that the fish aren't doing, the juveniles aren't doing one thing, they're doing multiple. And so it's time, I think, that we have to have some type of place to discuss what, the very foundation for how we're thinking about things. And we haven't done that in a long time. I'm not so sure that's, but I think it's important that we do, because right now, you look upslope and you think about it one way, and you turn down and look at the stream and you think about it in a very different way. And that hasn't been recognized or acknowledged, and we haven't asked why. Why do we do that? And I think until we do that, we're gonna be stuck in this, yes, it does, no, it doesn't type of thing. And that I look at it and think, wow, that's really cool, because I think differently. I have to say, one of the most incredible experiences I had professionally was the CLAMS project. This was coastal landscape analysis and modeling study, where we tried to do this integrated look at the coast range. And it would involve Tom and a whole host of other people, and we had aquatic people, and we were drawing, they were putting maps together and saying, oh, well, this is what the coast range looked like historically. And I'm sitting there thinking, wait a minute, these guys, I think they have this idea of this mosaic and changes and stuff. We had nothing that was parallel to that in the fish world. And they started thinking about, well, how did the fish persist in that environment? If we think about things being stable. And so it's something that is very seldom articulated or called for. We continue sort of bouncing down this road about arguing about whether it's good or bad. But the discussion should be, why do you say it's good? Why do you say it's bad? And understanding that, and then saying it's a time for a change in perspective.
There's a parallel to that in the terrestrial world. I think one of the biggest things that we've learned since our East Side studies and Tom's CLAMS work is that stationarity and then the suspicion of stationarity of conditions creates a very hard problem. And the interior dynamism is the key. And we have management systems for stationarity. We have management allocations. We put things in paddocks, and the assumption is we can keep them there. But there isn't any evidence in the system that we can do that, put things in a paddock. We can keep them longer and shorter, but we're actually not in control of the paddock. These processes are important. And so the question becomes, for the terrestrial and aquatic environment, what is a management system for dynamics? And how can you create management that allows you to be able to create transitions that are always, sometimes, and never on the landscape? Because nothing is assured when there's non-stationarity. Under climate change, the most important forcing factor is top-down climatic change, warming, drying, more windy, that sort of thing. What is a management system for non-stationarity, even of the dynamics? The dynamics themselves are shifting. So in a lot of ways, I think we have to almost hit the pause button and basically say, why are we doing what we are doing? Are we going there in the right way? What's the likelihood that we'll get the things that we want to deliver? And if we're off course, what are the fine tunings that we need to be able to do, and the discourses that we need to engage in to be able to get a different heading? What we're learning when we're doing climate change modeling on the terrestrial systems, that we're actually off the page. The historical range of variability is now impossible on most of the landscapes, and we have to prepare for a future landscape whose assembly rules can be understood, but it's non-stationary. So how do you get the stuff you want juxtaposed with other stuff on the landscape and do it in a more probabilistic way rather than a certain way by having management allocations that say, this lives here, this doesn't live here, because it's difficult to develop a delivery system for that right now, and that problem is increasing in severity. Michael?
So I have a question, but at first I want to express gratitude that you guys are pointing out that a lot of this has to do with the assumptions that we make about the nature of the world and the nature of value. I mean, it's almost like philosophy matters. Credit is the philosopher. Thank you for the promo, actually. But so Paul, following the logic of your description about cultural burning and then thinking about old growth forests, do you think it's safe to say that what we call old growth forests is is something that is the product of settler colonialism?
Yeah, that has deep roots in a lot of things, but fundamentally, yes. I think when European settlers, they came with values, philosophies, and an awful lot of that was underscored by religious beliefs that were embedded in the laws that they brought to the land and so forth. And so in an awful lot of ways, I think where your attention is, there you are. And you have to divert in some sense your attention to be thinking about other stuff. And there's more and more writing in the space right now about just basically saying, what's the construct, what's the value system that underpins our beginning, and very often our inability to be able to shift frame when the landscape is screaming at us, when the aquatic systems are screaming at us. I think we're at a place now, we're taking that kind of pause and reflection and understanding where our values come from, what's the possible, how do we actually become involved in a productive way with climate change? It causes us to examine our values very much and the principles that we abide by. And I think it's high time that we start having conversations that look like that.
We have a question from online. Julie, go ahead.
Right. Lynn from online asked, if we start allowing more of these wildfires, how do we work around the large amount of human development? So much of our land has some level of human development or capacity.
It's a problem and it's accelerating. All the easy ground is developed, and so we're going into hard places right now. Some of the hardest places that we could ever develop. In terms of using strategic use of spinning and burning types of methods, that's a hot place to be thinking about applying those kinds of things. And then in terms of governance structures, taking a hard look about places that are high fire danger and getting higher, and talk about where development just simply makes no sense to go. We're building developments where we can't protect people. So many developments are going up drainages, and there's no separate egress road, and firefighters are not going to go die to protect homes. And right now, about 70% of new housing starts are in high fire danger zones. And it's accelerating, it's exponentially increasing. So from governance, from community, county, larger governance structures, having a hard conversation about where should people be living and where we can protect them is incredibly important. And those discussions, we have WUI code, US and international WUI code, and we shop it, and it's meant to travel as a bundle. Implementing the WUI code, and if you do that, communities, including new developments, can be safe. But they're not, they're shopping those codes. And so people are putting themselves and their investments in harm's way. It's an important question that involves much better conversations between social science people, ecologists, counties, cities, those kinds of things about what's realistic going forward in the 21st century. And it's very different than last century. Yep, maybe.
Oh, you've talked a lot in the past about the topographic template, and Gordy, I know thinking about portfolios of things as organizing features have been part of your thinking too. As we start to look at this sort of future of thinking more dynamically, but needing both our philosophical roadmap as well as some sort of guiding features that are roadmaps for organizing what goes where in the geography of things. What would be that hybrid topographic template aquatic systems sort of loose roadmap to help at least guide some of these probabilities forward. If you're more likely to have this here, you might expect to have more of this here, a portfolio of this size of different stages of the river sort of system, sort of organized, at least as a general goal. Is there a roadmap idea that you two have been brewing to guide that kind of thinking?
Well, I think we've done something like that, where this is myself and Lee Bend and some others, Lee, who is an independent contractor. But we've done this analysis of the landscape, saying, okay, where are you likely to have landslides you're gonna reach the valley bottom, the stream? Where do you see, reaches of stream that if you remove the riparian vegetation, you're gonna see temperature increasing? Or as opposed to places where you can lose the riparian vegetation and you're not. And trying to get away from this one size fits all type of thing and deal, there's a lot of variation out there. We should be working with it. What my experience has been, man, the agencies, they don't want to know that because it's a lot easier to just have one way of doing things. And so there's a lot of analysis. Before I retired, I got money from the Washington office and we did an analysis of the downscale climate change projections from the Northwest. And so if you look at the impact of climate change, it's going to be a lot more variable than I think most people know. We did this analysis of the importance of the riparian areas, the temperature. We identified important floodplain areas. We identified landslide risk sources and stuff like that. From the California border to the crest of the Cascade, all the way to the Columbia River. We did it for $30,000 and we gave it to the Forest Service and they just, thank you. And off it went. Nobody even used it. And so it's like been a frustrating thing to think that, we can do this. We have the capacity to do it. It's been done. It's how do we get people to use it? How do we, how do we do that? That's been the frustration that I found in the agencies. And I don't want to say all agencies, but at least on the Forest Service side, they're really reluctant to do that type of thinking. It's easier just to, one size fits all and off you go. But I think we've got the tools, we've got the analysis done to be able to move in those directions. But we haven't seen the will to do it.
From my side, we're starting to make inroads in how to use the topographic template. So on the fish side, we're thinking about where does the sediment and wood budget come from within a watershed and which tributaries are likely to give it up. So we're modeling the hydrologically connected part of the landscape that has direct contact with main stem reaches or big trib reaches, where you've got lower gradient conditions that you want to be able to smatter every once in a while with sediment wood. And that footprint is really different than the peekaboo strips that we put along streams right now. And an awful lot of material comes from those. And so we're asking the question now as we're building these tools for the Eastern Washington forests is, can we think about terrestrial management that is basically setting up sediment and wood delivery specifically for the future? Because those are the big events that actually do so much work. A lot of it comes from mid and high elevation country. In terms of topographic template, we're finding out that there are geographic variants. So there is no one size fits all to think about topography. But you find in different geographies that there is a template for that geography. Adiabatic lapse rate matters. And we're calculating climatic water deficit, for example, on terrains right now for projects where we want to transition dry forest into non-forest conditions. And we're calculating it at a decadal scale right now out to 2100. So that over the decades of doing work, we can experiment with creating transitions and watch how they work. We're finding out that the difference between actual evapotranspiration and the potential of the vegetation really matters under climate change. So a tool like that is sort of intuitive for us, and it's now in our project level planning in the Eastern Washington forests. We find from geography to geography, there's a couple simple rules of thumb that are happening under climate change. Ridges tend to be hot and they get hotter. South-facing aspects are hot and they get hotter and they get drier. And so these are the places, if you're going to create credible transitions, opening those up into open canopy forests and more savanna-like conditions lower on the hillslope is really sensible. And we learn that from sort of the first principles we got from studying historical landscapes. But it's not repeating those landscapes on the ground. It's saying, what do you do with the learnings to adapt a landscape based on what seemed to work in the past, right? So, and then spatializing it takes a tool like climatic water deficit, a pretty high def terrain model, and trying stuff and then monitoring it really well. And we're doing photographic monitoring over time right now. The forests are contracting with a photographer to do before after conditions, and every 5 years going in and doing retakes, drone in on flat land. So things like that are going on. Under wildfire adaptation, this is my first climate change. I don't know. But the thought that I'm having is a lot of learning has to happen. So rules of thumb have to be tested and to find out just what their virtue is from place to place. You go into Klamath country and the terrain, we have an inversion season where the stuff above the inversion burns very differently than below the inversion. And as it turns out, it vastly influences the fire ecology down there. So terrain matters down there, but it isn't in the same way. So learning how topography works for you seems to be the government.
Yeah, thanks for that. I feel like those sort of, even though they're experimental sort of adaptive cycle guidance plans, but thinking through what there is an enduring feature to help guide through that topography piece and thinking through some of those tools as well. Gordy, you described, it's helpful to think about in our problem solving minds, where do we go from here with all these big ideas and thoughts about change and movement.
Right.
So.
Our indigenous partners basically say, we've been through a couple of climate changes and here's how we did it. Plants and animals are teachers. We walk alongside them and we try stuff. We keep the stuff that works. Very place-based, very, very bottom up. And if you stop and think about that mindset, plants and animals under teachers, when the dynamics are really shifting, it's a most clever move. Right?
Okay, most clever moves. Thank you.
There, let's go ahead and just have one more question, then I think we can adjourn to the reception. And we can continue to converse with our speakers and with each other. And I think this is the start of a really good and productive conversation. So why don't you go ahead with your question, sir?
So I'm trying to look at the kind of the current policy side and asking myself, how do we take what you're doing and transfer it into policy? And one particular question that comes to mind, I'm very concerned about this new focus that seems to be emerging around, let's protect the areas around our cities, and it almost seems like there's nothing we can do about the forest itself that's sort of removed from cities. And I guess the question is, how do you respond to those efforts, and are you optimistic that we can make some headway on the policy side?
It's slow. There's a lot of resistance to anything that's really innovative. It almost seems like at different levels of governance, the folks in the big chairs are eek and meek. But I think that talking about it, working the problem with people, working with lawmakers, taking the science out of the pages of journals and having conversations with people, those kinds of things are important. And there's some really cool work on the urban, exurban, and wildland problem. Dave Calkin, Rocky Mountain Research Station, Kamiko Barrett at Headwaters Economics, and colleagues. They've done several papers basically, and Jack Cohen, his lab through most of his career. They're talking about how you can tease apart the wildland and the WUI fire problem. And their argument, and I think it's pretty well supported, is how you solve, it's a PNAS, I think it's 2023. What they're basically making is a very strong argument that the levers for solving the wildland urban problem are very, very different, and you don't solve it in the wildlands, you still solve it in the buoy. And they give some really credible diagnoses that support that. The reference sections are replete with incredible work that supports their contention. And what they're advocating is tease apart the wildland and the buoy fire problem. They're mostly driven by different things. Do the things that are important in each space. Concentrate in the wildland, not on protecting homes, but on transitioning wildlands to conditions that can accept fire more readily. I really urge you to read that paper. Headwaters Economics has got another couple of pieces that are really excellent in that space, and then check out some of the references in the PNAS paper. And I think their arguments are really sound and worth exploring more deeply.
All right, well, thank you all. Hopefully we'll see